Okay, so sorry for the discontinuity. Today I'll start some theory of PDEs. So basically I'll be finishing off, I'll be covering uh, Laplace equation, Laplace equation, elliptical PDEs, heat equation, some variational methods. So don't worry what this is. So basically this is what is called optimization. And after some variational method I'll be discussing Sobolev spaces. I have discussed Sobolev spaces as such, but and Schwartz space again. I'll just recap some things. And extend some theorems. Okay. Then, after that, just a second. Okay. So, we have discussed about Sobolev spaces and everything in deep, but I would like to wrap up the discussion on Sobolev spaces and the Schwartz space with two theorems. And then we'll just go to specific PD such as Laplace equation and so on. Yeah. So we have this particular theorem. So basically what this says is that the space is complete. So I hope you remember what is completeness. If a sequence is Cauchy, then it must be convergent. If that particular space abides by that property, then it is said to be complete. Then it is, if the space L1P is complete, and if it is reflexive, then it is separable, means it has a approximating basis. In particular, H1 of omega is a Hilbert space. Okay, this is a theorem. Okay. So further, just extrapolating, I'm just giving some definitions on Hilbert space. Hm of R n is an Hilbert space with all u belonging to L2 of Rn, such that d alpha of u belongs to L2 of Rn for all alpha less than or equals to n. Right. And okay. So basically, if you take the derivative and the Fourier transform, b alpha of u of epsilon is equals to 2 pi I times mod alpha to epsilon power alpha into u hat epsilon for all epsilon in Rn. So it's just that I'm trying to define a H of space like that. So kind of like space where all half derivatives live. So basically, Hm of omega can be equivalently written as all u belongs to L2 of Rn such that u belongs to L2 of Rn and 1 plus mod epsilon square whole power half u hat also belongs to L2 of Rn. So with this I'll try to conclude the Sobolev spaces, and again I'll be recapping. Again I will recap Sobolev space before teaching optimization techniques. Okay. So now we have just talked about PDEs in an abstract fashion. So let us go to specific PDEs. The first PDE that we'll talk about is the Laplace equation. So all the physical phenomena such as heat, wave, Schrödinger wave equation, Maxwell's equations, are usually kind of somehow or related to the Laplace equation. So this is something that we begin our PDE study with. So once we understand the properties of Laplace equation, we can extrapolate things and go wherever we want to. Okay. So this is fundamental object of study. So definition of a Laplacian operator. So del u is equals to sigma I is equals to 1 to n, or dou square u by dou xi square, and Laplace. So I mean delta u is equals to 0 is the Laplace equation on some omega open and connected set. So basically a Laplace equation is is linear elliptical PDE. PDE is basically abbreviation of partial differential equation. I hope you know that by now. It's fine. So there is one definition. U in C2 of C2 is twice differentiable function. C2 of on domain omega is said to be harmonic if del U is equals to 0 on omega, subset of Rn, obviously, open set Rn. So this is an exercise that I give. Try to prove that Laplacian operator del U is invariant under rotations. I have basically given out, actually I have given out the proof in notes, just check that out. It's not that difficult. So I'll just be stating Laplacian operator in some polar coordinates. So del U dou square U by dou x square plus dou square U by dou y square plus dou square U by dou z square. This is something in Cartesian. In polar, del U is equals to dou square U by dou r square plus 1 by r dou U by dou r. Something, this equation that I work with a lot. This in plus dou square U by dou z square. This is in cylindrical coordinates, and spherical dou r square. Sorry, in spherical it is this way. One by r square dou by dou r of r square dou f by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou f by dou theta plus 1 by r square sin square theta dou square f by dou phi square. This Laplacian in spherical coordinates. Once we try to solve this, you kind of see some amazing equations. Okay, so I'll now start discussing about some interesting properties of Laplacian equations. So firstly, I'll discuss the mean value property. Of harmonic functions. Okay. So u of x comma y is equals to 1 by r square integral. I'll just keep this to be x naught y naught to be integral epsilon minus x norm square plus norm of eta minus y norm square u of epsilon comma eta. So what does this mean? So you have a set omega, right? And then you have a point x naught comma y naught, and you take a uniform ball around it, and you integrate the harmonic function on the unit circle. So what you get is that the value, you basically get the average value of the harmonic function in the unit ball. This can be equally written as 1 by 2 pi r times integral the circle u of s d s of sigma. So you take a circle, perform a a line integral, so you'll be getting the same average value, or else you just take out the, you just find out the average along the area or the circumference, you get the same value. That is what the mean value property says. Okay. So they are one and the same. I'll just prove that if you take a line integral along the circumference or the area over the circle and average or harmonic function over that, will be getting the same. So the reason is, you can write u of x comma y as, say, this according to the circumference thing, u of x plus tau cos theta comma y plus sin theta d theta for all tau, which basically, just you multiply by tau and integrate. So integral 0 to tau u of x comma y d tau, which is equals to 1 by 2 pi integral 0 to 2 pi integral 0 to r tau u of x plus tau cos theta comma y plus tau sin theta d theta d tau. This is nothing but 1 by 2 pi r square by 2. You get r square here, you just divide it. This is nothing but over the area times u of x comma y d area. So this can be equivalently written. So what this basically says is that you take a harmonic function and then you integrate across the circumference, and you integrate it across the area, you get the same value. Okay. So I'll just write the mean value principal in Rn. So u of epsilon equals to 1 by omega n minus 1 is the area of the unit ball in n minus 1th dimension, integral or so this is the area integral over the unit sphere in n dimensions. So this is the unit ball, and this is the integral along the circumference. So both of them are equivalent. So basically I have proved this theorem for 2 dimension, and I have written the proof of mean value theorem in arbitrary n dimensions in notes. So you can look into that, but in general it's better that engineers stick to intuition and just work on 2 or 3 dimensions as such, because So now I'll state a theorem. I'll state a theorem without proof. So if U belongs to C omega and satisfies harmonic property, then U is smooth and harmonic on omega. I'll just state the theorem without proof. So another theorem. If U belongs to continuous functions b of epsilon comma r, then there exists an estimate is harmonic on unit ball. Then is less than or equals to n by r module. So this gives an estimate on things, estimate on the derivative. So basically your harmonic function is smooth and all the derivatives, they don't blow up. It's a good function. Okay. Now I'll write a theorem. So a bounded harmonic function on Rn is constant. So how do we prove that? So from the previous theorem, dou u by dou xi at x naught, should be less than or equals to n by r u of x naught, right? Mod of x naught, and I can take r to be infinity because it's on the real line. So all the derivatives are equal to 0. Because all derivatives are equal to 0, then the harmonic function must be constant. Okay. I have proved these theorems. So this is the generalized version of the previous theorem. Suppose U belongs to it belongs to set of continuous function around a unit ball and is harmonic in the ball. Then for any multi-index alpha, dou I d alpha of u must be less than or equals to n by rho times mod d alpha of u. This is a general estimate. What's happening? I'll just state a lemma. If U belongs to L1 log of omega is weakly harmonic, in the sense that integral omega u del phi 0 for every phi belongs to CC infinity function implies U belongs to C infinity of omega and is harmonic omega. So kind of like your weak convergence implies strong convergence. So Okay. Now I'll start with the maximum principles. Let u omega to Rn be a continuous function such that you can extend it on the closure of omega. Okay, so can I increase this? Okay, so let u belongs to some continuous functions in omega such that it can be extended to the closure of omega. So let u belongs to C of omega bar implies u attains maximum on the boundary. Okay, and let's go through this. So I'm just going to state the theorem again. So this is called the weak maximum principle. Just a second. So what the weak maximum principle says is that, just a second. Just a second, I'll just be back.